Hi, welcome back. Hope you're doing well. Today we're going to talk about Google PageRank. But let me just remind you of the two important theorems from last time, Perrons Theorem and Forbinius Theorem. So Perrons Theorem holds for any positive matrix, so all of the entries are positive. Positive matrices have a unique dominant eigenvalue. So an eigenvalue that is larger than all the others in absolute value. It's positive, and it has a positive eigenvector. And the algebraic multiplicity of the dominant eigenvalue is 1. So in fact, there's sort of like a unique dominant eigenvector. There's only a one-dimensional space of eigenvectors. And in fact, no other eigenvalue has even a non-negative eigenvector. If in addition you're actually Markov, then that dominant eigenvalue is actually 1. So all the eigenvalues are in absolute value less than 1, except for the dominant eigenvector, dominant eigenvalue, which is 1, for which we get a positive eigenvector. And also, if you're positive Markov, if you start with any non-negative vector, and you multiply by a bunch of times, you will tend to the direction of the dominant eigenvector. So some scalar multiple times the dominant eigenvector. Okay, so that's if you are just if you're a positive matrix, you can say these really strong things about the eigenvalues and eigenvectors by Perrons theorem. Forbinius' theorem is a bit weaker because it deals with non-negative matrices, so some of the entries are allowed to be 0. Such matrices will have a dominant eigenvalue with a non-negative eigenvector. The dominant eigenvalue will be non-negative, and it might not be the unique biggest thing. So there could be other eigenvalues that are equal to the dominant one in absolute value. But again, if it's Markov, then the dominant eigenvalue will be 1. So you're always guaranteed for a non-negative or a positive Markov matrix that the largest eigenvalue will actually be 1. And we also discussed how if you're not necessarily positive, but some power is positive, then you still get this uniqueness of 1 as the unique dominant eigenvalue. Okay, so today we're going to apply that this theorem essentially to develop the notion of Google PageRank. But before we can do that, I want to introduce some terminology from graph theory, which will pop up at various points during this course. Okay, so quick graph theory diversion. Okay, so a graph is just a collection of vertices and edges. It's almost the most unstructured mathematical object there is. So a graph G, let's call this a definition. A graph G is a collection of vertices, or sometimes they're called nodes. We'll always label them 1 through n. So we're also assuming that graphs are finite in this class. Of course, there are infinite graphs, but in this class, all graphs are finite. And edges, which connect pairs of nodes. Okay, so let me just draw an example. I'll draw the example in the notes, I guess. Why not? So we'll take the convention where we'll draw our nodes as circles and label them with their number. So this is a graph on 3 vertices. And then edges are just, we'll draw as lines between the nodes. Okay, so if you have an edge from 1 to 2, you just call this edge the set containing 1 and 2. So you can write any edge as just the set containing the 2 nodes that it connects. So this edge we could call 2, 3. Okay, so if I want to denote this whole graph, we denote a graph by a pair. First you list the vertices, then you list the edges. So in this example, maybe I should have made it a different color. The graph G, if I call this thing G, first you give, it's an ordered pair. First you give its vertices. So this says that it's a graph on 3 vertices, 1, 2, and 3. And then I'll list all of the edges in my graph. I'll list them as a set, of course. It's a set of edges. So this is the set of vertices, this is the set of edges. And so given any graph, you can write it down in this way, right? This encodes all the data of the graph. Here are the vertices, here are all the edges in the graph. Okay, now to a graph, we can also associate a matrix. To any graph G, we associate the adjacency matrix, which is an extremely important matrix. Okay, what is the adjacency matrix? I guess let me write the definition in full gory detail. The adjacency matrix also encodes all of the data of a graph by telling you where the edges are. Okay, so the adjacency matrix of a graph G on n vertices is an n by n matrix whose rows and columns are indexed by the nodes. Right, 1, 2, 10. Right, so you have a 3 by 3 graph. You have a graph on 3 vertices. There's a 3 by 3 matrix, and you think of like the first row as corresponding to the first vertex or node. The second row is corresponding to the second node. The third row is corresponding to the third node. And you let define A as follows. Basically, you will let Aij be 1 if ij is an edge, 0 otherwise. So basically, you just put a 1 in a row and a column if there's an edge from that row vertex to that column vertex, right? So here was our graph. If this is our graph G, then the adjacency matrix is a 3 by 3 matrix, right? So you think of this as being indexed by 1, 2, 3. This being indexed as 1, 2, 3. And then you just put a 1 if there's an edge from that row to that column, right? So there's no edge from 1 to 1. There is an edge from 1 to 2. So you put a 1 there. There's no edge from 1 to 3. 2, there's an edge to 1, and there's an edge to 3, but there's no edge to itself. And 3 has just an edge to 2. Okay, so this is sort of definition by example. This is as much as you need to know about it. I mean, if you understand this example, then you understand the definition of the adjacency matrix. Okay, note that for any graph, AG is always non-negative, right? Because there's no such thing as because we filled it up with zeros and ones based on if there was an edge or not. And it's not Markov. But since it's non-negative, Forbinius' theorem still does apply, so we should expect that it would have like a dominant eigenvalue with a non-negative eigenvector. And this kind of thing we should probably actually do in Julia. So let me switch. Right here we have Julia again. So using linear algebra, I want to write down my matrix. So in this case, it's 0, 1, 0, 1, 0, 1, 0, 1, 0. So I'm just entering the rows. There is my matrix as promised. And then we can take a look at the eigenvalues of A, make a look at the eigenvectors of A. Okay, so if we look at the eigenvalues, this second eigenvalue is a tiny number, so that's actually probably 0. And each of these numbers looks like the square root of 2. So it looks like root 2, 0, minus root 2. And you can actually do this example and find that the characteristic polynomial is in fact t minus 2 times t, so t squared minus 2t. You could actually do it. Okay, so notice that there is a largest eigenvalue, but it isn't unique largest in absolute value because there's one that's negative root 2. Okay, but this dominant eigenvalue should have a non-negative eigenvector, and it does, right? So this looks like 1/2 root 2 over 2, 1/2. Or you could rescale it and make it 1 root 2, 1. Or in the notes, it's rescaled as root 2, 2 root 2. So they multiplied this whole thing by 2 root 2. This one has not, this eigenvector is not non-negative. It's like negative root 2 over 2, 0, root 2 over 2. And then this one also has not an eigenvector that's not non-negative. Okay, so this thing has a positive dominant eigenvalue. It's not 1 because the matrix wasn't Markov. It has another eigenvalue that's as large as the dominant one in absolute value. And the eigenvector corresponding to the dominant eigenvalue, it's supposed to be non-negative, and it is non-negative. In fact, in this case, it actually happens to be positive. Okay, so let me switch back. Okay, so this was just the definition of an adjacency matrix. Graphs are, the study of graphs is an extremely important subject. The adjacency matrix is one of the most important matrices that you can associate to a graph. And so if you want to understand graphs, then you want to understand their matrices. Basically, you want to know a lot of linear algebra. Okay, but now let's move on to Google PageRank. Okay, so what is Google PageRank? Google PageRank is the algorithm that was invented by Larry Page and Sergey Brin when they were CS grad students at Stanford. And they were trying to come up with a better search engine, right? This was before Google existed, maybe before some of you were born, but not before I was born. Think of the problem that they were facing, right? What they needed to do was they needed to figure out a way to find relevant web pages. The internet is this humongous thing. It's got all this information on it. You want to know about something specific. How can you go about finding pages that are relevant to what you're interested in? It's a hard problem. Okay, and there are some really naive ways, right? So you could try to sort of index keywords for every page somehow, or index the text on every page. And then when you search, you could look for that keyword, and you could just return all the pages that have that keyword, say. But then how do you order them? Also, if I just create a web page that just spans the keyword a bunch of times, somehow that shouldn't count as like an important hit. So it's not so obvious what to do. And they came up with sort of a very elegant solution that actually, at this point in the class, we can totally understand the Google PageRank algorithm. Okay, so the first thing to do is to think of the web as a directed graph. Okay, so let's think of the web as a directed graph. Okay, so what is a directed graph? A directed graph is just like a graph, except the edges have direction, right? So in our definition of graph here, the edge was just connected 1 and 2. It also connected 2 and 1. There was no directionality to the edge. I didn't draw it as an arrow. A directed graph, the arrows have direction. And how do we represent the web with a directed graph? Well, let's imagine that there's 6 pages on the web, or maybe there's only 6 pages that are relevant to our search. Let's draw an example web graph, and let me tell you what it means. Okay, so I'll draw it just like in the notes so that I don't get confused and that you don't get confused. Okay, so what we'll do is we'll represent every page by a node. And we'll represent hyperlinks between pages with directed edges. Hyperlinks between pages via directed edges. Right? Because hyperlinks by nature are directed, right? Page 4 links to page 5, but page 5 might not link to page 4. It also could, right? So this is also like a valid web graph where 3 and 5 link to one another. Okay, and the basic insight of Larry Page and Sergey Brin is that information is carried in the hyperlinks between pages, right? If a page hyperlinks to another page, somehow it's saying that this other page is important. So there is some information in this graph about which pages are the most important. Now, you don't want to do something like just counting the number of links to a page, right? That's, again, another naive thought, because if you did that, then what I would do is I could just make a billion websites that all point to my page, which maybe isn't very relevant, and then that would count as a billion for me, and then it's just, yeah. Of course, search engine optimization is actually a thing, but that's a really easily beaten system, right? But there's sort of a second step, which is it's not just the number of pages that link to you that sort of say that you're an important page. It's also the importance of those pages, right? So an important page should look like it will have a lot of links coming to it, and those links are also coming from important pages. Now the question is, how do you extract that information from this graph or from the matrix? Okay, and the really key insight of the Google PageRank algorithm is actually the following. It's imagine that you have a bunch of random surfers, random people on the web that are distributed somehow among the pages, right? So you have a bunch of people, some people at page 1, some people page 2, 3, etc. At each time step, have them all randomly click a link on their page. So if for all the random surfers who are on page 1, they all end up at page 4 because there's only one link to click. Right? But of all the random surfers that are on page 4, sort of a third of them end up on page 2, a third of them end up on page 3, and a third of them end up on page 5. So let's imagine that we have some population of users on this web graph, and at each time step, they randomly click a link. The insight behind Google PageRank is that over time, they should congregate at the more important or the more relevant web pages. Why is that? Well, for one thing, if there's more links to you, there's more ways to get to that page. Right? But also, because the surfers tend to congregate at the more important pages, also links from important pages matter more, because the links from important pages will sort of send more people over to you. And hopefully you can kind of see that this is some kind of Markov process. We have 6 states, and at each time step, people move between the states. That'll be governed by some matrix, which we'll discuss in a second. And then we want to understand the long-term behavior of what will happen to the states, right? So maybe you start off with 1/6 of the people at every one of these 6 pages, and at each step, they randomly click a link. You evolve that system over time, and you see, okay, where do the people accumulate? Based on some stuff that we saw in the last lecture, if the matrix were positive and Markov, they would uniquely tend, no matter where you started, they would uniquely tend to a single vector of states. And that vector of states is like what we'll call the PageRank vector. Okay, so the key insight is if we model this process with people randomly clicking on links, then over time they should accumulate at the more relevant pages. Okay, so that's the general idea. Now let me tell you about what the actual algorithm is, and it's slightly different from what I said to account for some issues. Okay, so in particular, if I was just to do what I just said, then you wouldn't get a positive matrix. Because there's no chance of moving from state 1 to state 2, right, in one click. And then we wouldn't necessarily get a unique dominant positive eigenvector. So we need to remedy this a little bit, and you remedy that by throwing in a very small chance that users would teleport from one page to a random page on the web graph. Okay, so what we're going to imagine, and again, I'll write something down in a second. What we're going to imagine is that we have a bunch of random surfers on this web graph. They're distributed amongst the pages somehow. And then at every time step, they all roll a dice. A die? Yeah, die is singular, right? They all roll a die. If they roll 1 through 5, what they'll do is they'll randomly click a link on the page. right? So most of the time, they'll follow the links of this web graph. But if they roll a 6, then they will randomly go to another page on the internet. What this will account for is this will allow us to go from any page to any other page, and will ensure that our matrix is positive Markov. And so, since it's a positive Markov matrix, it will have lots of nice properties that we'll leverage into defining this PageRank. So I haven't told you how to get the Markov matrix yet. So let me tell you how to do that. So we imagine random surfers. Distributed throughout the web graph, or distributed amongst the pages. Right, so in our example, there's 6 states. At each time step, each user does one of 2 things. Either 1, so follows a link, with probability, or with like a random link on the page, with equal probability for each link, or teleports to a random page. Okay, and what I'll do is I'll say, okay, 5/6 of the time they'll follow a link, and 1/6 of the time they'll teleport. Okay, you can actually change these proportions to whatever you want. I think a typical value used, like in the original paper maybe, is like 0.15 and 0.85, but these numbers are pretty close to 0.15 and 0.85. Basically, this just tells you how much you want them to follow the links versus how much of a chance you want them to teleport, right? So of course, if you made like this 1 and this 0, you would get no information. Yeah, so you can adjust these values, and it probably won't change your PageRank that much, actually. Okay, and from this, I'm going to construct a matrix from my web graph. How am I going to do it? So we're going to construct the PageRank matrix. A, which has entries aij as follows. We'll let aij be the probability of moving from page J to page I under this process. Okay, in other words, each row will represent the probabilities of landing on that page, and each column represents the probability of clicking away from that page. Okay, so let me define this via an example, which is this example. So we'll have a 6x6 matrix whose rows and columns are indexed by our nodes. Okay, and each row represents the probabilities arriving at that node. So probability of arriving. And each column represents probabilities of leaving. Okay, so let's think of the first entry, which is A11. Okay, so the question is, what probability is it that you go from page 1 to page 1? The only way to get from page 1 to page 1 is by randomly teleporting, right? So there's a 1/6 chance that you randomly teleport. And then within that 1/6 chance, there's only a 1/6 chance that you actually randomly teleport to vertex 1. So this first entry is 1/36. Okay, let's go down this column, thinking of a person starting at 1 and where they could end up. Okay, again, the only way to end up at 2 is to randomly teleport there, because there's no link from 1 to 2 in one step. So similarly for 2 and 3, there's a 1/36 chance of moving from node 1 to node 2, or from node 1 to node 3, because you have to randomly roll a 6, and then you have to teleport randomly to the pages. What about going from page 1 to page 4? Okay, well, 5/6 of the time, when you're clicking a link, you will go from page 1 to page 4. There's also some chance that you teleport there, right? So A for 1, so 5/6 of the time, it's probability 1, plus 1/6 of the time you randomly teleport there, so you get 31 over 36. Similarly, to go from page 1 to page 5 and page 1 to page 6, all you can ever do is teleport, which happens with probability 1 over 36. Okay, and notice that the way that we've set this up, the column sums to 1, because the column represents all the probabilities of leaving vertex 1. And at every stage, you leave vertex 1 and end up maybe back at vertex 1, but you leave vertex 1, so all these probabilities sum to 1. Okay, what about vertex 2? Vertex 2 is sort of the same story, except it can only end up at 1 by clicking. Anywhere else, it would have to randomly teleport, right? So the second column will look like 31 over 36 and then 1 over 36 all the way down. I guess the first interesting one is vertex 4. So the fourth column, the chances of ending up at 1 or 6 are still 1 over 36 because you have to roll the dice and then you have to randomly teleport there. But now, for the remaining 5/6 of the time, the users at vertex 4 will click a link on the page. So 1/3 of the time they'll go to vertex 2, 1/3 to 3, and 1/3 to 5. So to go from A42, it's 5/6 of the time they'll click a link with 1/3 probability. And then plus there's always a chance of random teleportation. And so what you get here is you get 11/36. And that will be true going to page 3 and page 5, but still only a 1/36 chance of ending up at page 4 because it can only teleport there. Okay, but as you do this process, one thing to notice is that in this example, link 6 is actually kind of special because link 6 has no outgoing links, right? Which means that if you imagine a random surfer, then once they get to 6, they would be stuck there, other than the random teleportation factor. If you're not random teleporting, it has to click a link and there's no link to click. Okay, this is what's called a dangling node. And we need to do something special with this because we don't want our servers to get stuck because there's no links to click. So if they ever reach a node where there's no links to click, then what you do is you just randomly send them to a page with equal probability across your network. Okay, that means that this last column is special. It's just all 1/6. Because otherwise, I guess technically we would have to say that we should put zeros here. By the definition, I said that it's the probability of clicking a link to end up at another page. That would be all zeros, but that wouldn't be a stochastic matrix anymore, right? So we need to do something special for dangling nodes. We redistribute. Okay, but now what we should do is we should actually try to understand this matrix, which is best done in software. So let's now switch to Julia. Okay, so by the magic of television, what I've done is I've opened Julia. I've said I want to use linear algebra, and I've entered the PageRank matrix that we were just talking about, right? So for example, the first column was 136, 136, 136, 31 over 36, 136, 136. Okay, so let's enter this matrix into Julia. There it is. And notice that this is a positive Markov matrix. Okay, it's a Markov matrix. It's column sum to 1 because we made each column represent the probabilities of where you would end up after you left that vertex. So that will always sum to 1. And the reason that it's a positive Markov matrix is because we made sure that there was some chance that you went to any other vertex from any vertex. Even if it's a small chance, if you just click the links from vertex 1, you can only get to vertex 4, but because we randomly teleport, there's a small probability of ending up anywhere. And so here we get a positive Markov matrix. And that's very useful because therefore the Forbinius theorem holds, right? So from this, I should expect that there should be a dominant eigenvalue, which is actually equal to 1 because it's Markov. So 1 should be our largest eigenvalue, and it should have a unique dominant eigenvector in the sense that the eigenspace 1 is one-dimensional. So let's take a look at the eigenvalues of A. And notice that, just like I said last week, even if you start with a very nice real matrix, you could definitely have non-real complex eigenvalues, but they'll occur in conjugate pairs, which is what happens with these first two eigenvectors here, right? So these are complex eigenvectors that are conjugate pairs, and these other ones are real, right? So the I, M in Julia represents the imaginary number. And 1 is, in fact, the largest eigenvalue in absolute value. That holds, by the way, even for these complex eigenvalues. You could take the modulus of these complex numbers by summing the squares of the components and taking the square root, and it would still be smaller than 1. So that theorem about having the largest eigenvalue be 1, it means for a complex number, you take the modulus of the complex number. And now, if I look at the eigenvectors, we should expect that the dominant eigenvector will be a positive, that there should be a positive dominant eigenvector. So let's look at the eigenvecs of A. And indeed, notice that this last, so the eigenvectors here are the column vectors, they correspond in the same order. This last one is a positive eigenvector. Okay, now what does this mean? This means that if you take any scalar multiple of this vector and you multiply by the matrix A, it will be fixed. It has eigenvalue 1. So now let's think about which scalar multiple of this vector I should take. Let's take the scalar multiple of this vector whose entries sum to 1. Okay, so let me quickly do that. Let's pull out the dominant eigenvector. So dominant eigenvec equals, I want to take this 6th column out of here, so I think I do that with colon comma 6, like this. Good. So this, I'm just pulled out the dominant eigenvector. But of course, any scalar multiple of this will also be an eigenvector. So let's take the sum to be the sum of the dominant eigenvector. Okay. So dom sum equals sum dominant eigenvec. I can't use the variable name sum. So it's this real number. And now let's call our PageRank vector the scaled dominant eigenvector so that its entries sum to 1. Okay, so all I've done is I've just scaled this vector so that the entries sum to 1, right? So now if I take the sum of my PageRank vector, I should get 1, right? Which I do. Now, this is an eigenvector with eigenvalue 1, and I can think of this as a probability distribution amongst my nodes. In other words, I can think of having this proportion of people at vertex 1, this proportion at vertex 2, etc. This would account for all of the random surfers. And since this is an eigenvector with eigenvalue 1, that means if I start with this proportion of people distributed amongst my nodes like this, and I go forward one time step, that means I multiply by A, then I'll get the same proportion of people. So people will still move around, but the probability that they're at any given node ends up being fixed. So what this says is that if you start with any distribution of people amongst your nodes, and they all click or teleport according to this scheme, Perrons Theorem says that eventually they will tend toward this probability distribution. And therefore, the way that you rank the importance of the pages is you just rank them by the probability that a random surfer will end up there in the long run. Okay, so what this says is that, by the way, this thing is called the PageRank vector, and right, these are all real numbers, so they represent probabilities. So it's the scaled dominant eigenvector for the PageRank matrix. Okay, and what you do is you just rank the pages in order of this probability vector. So this says that 1 is the most important page, then 4, then 3, 2 and 5 are tied, and 6 is the least important page. Okay, so what are some points that I want to make here? So first of all, this is basically just linear algebra, at least the idea of it. Of course, there's implementation challenges, right? Because the web graph is humongous. How do you store this data? How do you in fact, like if I type in a search, how do I come up with the web pages that are relevant to that search before I even try to rank them, right? How do I even get a list of a web graph to rank? But the idea, which is a very powerful idea, it still forms the basis of lots of the technology at Google, or in terms of ranking anything, right? So like there's ways to rank scientific journals, for example, where you let the directed edges be given by the number of citations from one journal to another. And then you can sort of, turns out to be a pretty robust way to rank the importance of things if you have some notion of linking between them. But the idea is one that we can totally understand. We just assume that we have a population of people randomly distributed that sort of randomly click links, and where they accumulate, they should accumulate at more important or more relevant pages. Another thing to note is we can even use Julia to compute, because it would be monstrous to try to do this thing by hand. Okay, so whether you use Julia or MATLAB or whatever you want to use, you want to be able to compute things like this. So I mean, I'm just learning Julia now. The things that I wanted to learn how to do, I just Googled them. Sam, your TA, has more experience because he's taught and TA'd this course before. You can figure out with one another how to use Julia in the best way possible. Okay, now I've switched back to this view because I just want to talk a little bit about computational complexity of finding the PageRank vector. So, how would you go about finding the PageRank vector? Well, we said that what you want is you want the dominant eigenvector of the PageRank matrix, right? Which, you know, since it's a positive Markov matrix, is an eigenvector with eigenvalue 1, and you know that's a one-dimensional space of eigenvectors. So you find any basis for that, and then you scale it so that it sums to 1, right? Actually, to find the ranking, you don't even need to scale it, right? So how would you do this? Let's talk about the computational complexity of it. Right, so let's suppose that A is the PageRank matrix. Again, that's the matrix that we came up with all 1/36ths in it. And let's suppose it's n by n. And keep in mind that n here is going to be, in general, huge, right? When you do a Google search, you get like hundreds of millions of hits. Right, so like, say, on the order of 100 million. So a humongous matrix, although it is quite sparse. There's lots of zeros, right? Because most of the pages don't link to most of the other pages. So it's a huge matrix, but it's sparse. Both of which are important. And if you're solving a real world problem, it's important to know what kinds of matrices you're actually going to get. Well, what's the math 308 way to find the dominant eigenvector? It's to take the null space of A minus I, right? So the 308 way is you want to find a basis for the one eigenspace. That's the null space of A minus I, which is, again, 100 million by 100 million matrix. That's also quite sparse. Well, how do you find the null space? Again, the 308 way is to take A minus I and then row reduce it to echelon form. So how many operations does that take? Well, we can get a pretty rough estimate. For each row in your matrix, right? It's like you'll find a pivot in that row, and then you'll use that pivot to kill everything underneath it, right? So for the first row, you'll have to do n operations. So that for the next row, you'll have to do roughly n minus 1 operations. So for each row, you'll need to do roughly for each row you'll need to do roughly n, then n minus 1, down to 2, down to 1 row operations. And there's n rows. So this thing sums to roughly so this thing sums to roughly the number of row operations you'll have to do. And this is just the sum from 1 to n. So you'll have to do roughly n choose 2, or n times n minus 1 over 2 row operations. Roughly, right? So we might as well say roughly n squared. Okay, but each row operation that you do requires you to do roughly n operations, right? Because one row operation, you need to do a division or multiplication or a subtraction with each of the n entries in the row. So roughly, I mean, this should give you a rough idea that row reduction to echelon form takes roughly O of n cubed. And remember, n is humongous. So O of n cubed is not great. It's not terrible either, but it's not great. Okay, but this is where actually the other part of Perrons theorem comes into play. And it's a part that we haven't really talked about yet, and it's part 6 of Perrons theorem. What does this say? If you start with any non-negative vector, and you keep on multiplying a by that vector, you should converge to the dominant eigenvector. You start with any random vector, you keep on multiplying by a, it will eventually head toward the dominant eigenvector. Now, why is this good? Because multiplying a matrix by a vector takes way less operations, right? So if you take a an n by n matrix and you want it, and you take a vector, call it w naught in Rn, to compute a w naught, how many operations does this take? Each row, you need to take the dot product with w naught. But taking the dot product is only n operations. And you have to do that n times. So this takes roughly O of n squared. So multiplying by a matrix once takes O of n squared, whereas row reducing a matrix takes O of n cubed. And a very nice thing is that if you have a sparse matrix and you start with, in practice, you can just let W naught be the all ones vector. So in other words, you start with an equally distributed population on your graph. Then actually, it converges quickly to the PageRank vector. That's the thing that's been studied. That's beyond the scope of the class to prove that it converges quickly. But roughly, you can do it, I don't know, in like 50 multiplications, 100 multiplications. So 50 times n squared is way better than n cubed when n is 100 million. Okay, so this 8kw naught converging to this dominant, right? I mean, this thing is the PageRank vector. Happens quickly, certainly faster than 100 million. And this is in practice how you would actually find the PageRank vector. You just start, I mean, you could start with any non-negative vector you want. It turns out that in general, it's best to start with the even distribution, the uniform distribution amongst on the web graph. And you multiply by a, which is computationally cheaper than row reducing a. You do that until you converge relatively close to the PageRank vector, and then you have at least roughly the PageRank vector. So this sixth part of Perrons theorem, which to me seems like the least useful part somehow, is actually maybe the most computationally useful part of Perrons theorem, because it allows you to find, or at least approximate, the dominant eigenvector by doing a lot fewer operations. Okay, and in general, computational complexity of things in linear algebra is a really surprisingly interesting subject. Okay, so for example, I just want to talk about matrix multiplication. Okay, there are people, I have friends who have a research career studying fast matrix multiplication, which is kind of unbelievable. It's sort of unbelievable that we don't fully understand matrix multiplication in terms of computational complexity. Okay, so suppose that A and B are two n by n matrices. How many operations does it take to multiply? Okay, well, let's think about this for a second, right? You have, I mean, I can even do it with two by two matrices just to illustrate. When you want to find the product of these matrices, what you have to do is you have to dot every row of A with every column of B, right? So there's two rows of A, there's two columns of B, so you need to dot n rows with n columns, and then each of those dot products takes n operations, n multiplications, right? So to find the product takes roughly O of n cubed if you're doing it via the method that you learn in 308, right? The method that all of us do by hand. this should make sense, right? Because to multiply just by one column took O of n squared, and doing a matrix multiplication like this is like doing n columns, right? So it should take n times as long. Now, what's the theoretical speed limit? What's the speed of light here for how fast? Because I should say that this is the school book method. Like what's the theoretical speed of light here? Well, the matrices have n squared entries, and you need to do something with every single entry. So there's no way you're ever going to get faster than n squared. You have to do something with each of the n squared entries of A, right? So the speed limit here is O of n squared, right? O of n squared is roughly how that's this n squared is the size of the outputting matrix, right? So the speed limit here is almost as fast as you can read the matrix is how fast you can multiply. Now, a really unbelievable fact is we don't know what the best possible algorithm for matrix multiplication is. So the best possible algorithm should be O of n to the something, where k is between 2 and 3. Okay, you could put the less than equal to, it doesn't really matter. And this is an active area of research to find faster and faster algorithms for matrix multiplication. So let me share with you some Wikipedia pages, which I encourage you to look at on your own. Okay, so I'm just on the Wikipedia page for computational complexity of mathematical operations. Okay, so matrix multiplication, that's the first row of matrix algebra. It's also the, like, these things are the most well-studied things. Also, by the way, notice here it says, can I point here? I can kind of point, right? Yeah, Gauss-Jordan illumination is O of n cubed, like I said, or like I roughly laid out, right? So matrix multiplication, the schoolbook algorithm is O of n cubed, but then there's this algorithm, Strawson's algorithm, that's O of n to the 2.8 something. So this is due to Volcker-Strawson. And you can read about it. You can, in fact, you can understand this Wikipedia page. Wikipedia pages in math are often quite technical. They're actually written by experts. But essentially, if you're doing two by two matrices, instead of doing 8 multiplications, you can do 7 multiplications via this formula. And then for every bigger matrix, you can break it up until it gets to 2 by 2s, and then you can apply this algorithm to each 2 by 2 and save 1 multiplication out of 8. And that's how you get this 2.8 whatever. What did it say? 2.807. So to be honest, it's a little bit amazing that you can do better than O of n cubed. If I had to guess before, if I was like a caveman who just discovered matrices and I would have to guess, I would have guessed that you can't get better than O of n cubed, but you can. You can save a multiplication on 2 by 2 matrices, and then you can break up. You can continually bisect your matrix until you get the savings on every little piece. That takes you down to 2.807. Then there's this Coppersmith-Winograd algorithm, which is 2.375477 for the exponent. But notice that what this says is the asymptotic running time. In other words, if n is huge, then Coppersmith-Winograd is better than Strawson. But there's a large constant factor, and so for like relatively smaller matrices, actually Strawson's algorithm is actually still better, or more practically used in practice. Okay, and people improve on this. I mean, if you look at this paragraph here, starting with in 2010, man, okay, you can't really see. Oh, I can point out on it here, right? This bound is continually being improved. So at least as of this Wikipedia page being edited, the world record is actually 2.3728639. There's a Quanta magazine article, which Professor Thomas shared with me. So maybe I'll post the link to Canvas, or maybe I'll post a printout of it to Canvas, discussing what was at the time, and I still believe is the world record for what the exponent on the matrix multiplication is. Okay, but this is actually an active area of research, and it's very interesting to me that we sort of don't know what the correct exponent is. I think maybe people are starting to believe that we've sort of squeezed all the blood out of this rock. This exponent is getting as close to as good as it can be with just these methods, but maybe there's some other method that can dramatically improve it, or maybe this is the best possible. We don't know. So I think that's very interesting. And if you're taking this course, I hope it's something that you find kind of interesting as well. Yeah, so hopefully you found this lecture fun. Next week, we'll start talking about orthogonality and projections, which is a little more like standard linear algebra stuff, but we want to develop this because it's not covered in 308 in order to talk about more applications coming soon. All right, so see you then.